NASA's twin Voyager probes, launched in 1977, captivated the world with historic journeys to Jupiter, Saturn, Uranus, and Neptune. Both probes continue their journey into interstellar space 45 years later. Researchers, some of whom are more recent than the spacecraft, are currently using Voyager data to unravel mysteries within and beyond our solar system. In many ways, NASA's twin Voyager spacecraft have evolved into time capsules of their age, containing around 3 million times less memory than contemporary cell phones and transmitting data at a rate approximately 38,000 times slower than a 5G internet connection. Each spacecraft even has an 8-track tape recorder for data storage. Despite these limitations, the Voyagers remain at the forefront of space exploration. So, what are they doing right now? What will the Voyager spacecraft encounter next? Let's find out. These two remarkable spacecraft might never have launched if not for a rare alignment of the 4 largest planets in our solar system. Thanks to this fortunate coincidence, each spacecraft could gain speed from the gravitational pull of each large planet it passed, as if pulled along by an invisible rope. However, this alignment only occurs once every 176 years, so a spacecraft had to launch by the mid-1970s to reach the planets while this alignment persisted. NASA seized this once-in-a-lifetime opportunity by creating 2 identical spacecraft. Voyager 1 and Voyager 2, which launched just 15 days apart in the summer of 1977. Operating in space for nearly 45 years, they send data back to Earth daily from the solar system's farthest known regions, having outlasted every other spacecraft in history and traveled farther. According to current understanding, the Voyagers have crossed the boundary between the Sun's influence and the rest of the galaxy, entering interstellar space. They are the first human-made objects to do so, and will likely hold this distinction for many more decades, not a bad record for missions initially designed to last only 4 years. In the early years of their mission, the Voyagers' observations of Jupiter's and Saturn's moons astonished researchers. These moons were once believed to be as inactive and crater-pocked as Earth's moon, but the Voyagers revealed otherwise. They found active volcanoes and fractured ice fields on these worlds. Voyager 2, in fact, became the first spacecraft to fly by Uranus in 1986 and later Neptune in 1989, making it the only spacecraft to visit these planets. Today, the Voyagers continue to surprise physicists with discoveries in the uncharted regions they explore over 12 billion miles from Earth. As these incredible journeys near their end, NASA has begun shutting down non-essential systems to extend their energy until around 2030. This bittersweet period affects many scientists who have worked on the mission since its inception, seeing it surpass even their highest expectations. Voyager 1 reached Jupiter 546 days after its launch in March 1979, followed by Voyager 2 in July. Both spacecraft were designed to be stable platforms, with Vidicon cameras using red, green, and blue filters to capture full-color images. Rotating at a speed 15 times slower than a clock's hour hand, they minimized visual blur as they traveled through space. As they neared Jupiter, the spacecraft began transmitting images, sparking enthusiasm among the crowds at NASA's Jet Propulsion Laboratory JPL. Io, one of Jupiter's moons, surprised everyone by appearing in vibrant color, shattering assumptions that all moons in the solar system were dull and cratered. The Voyagers soon discovered moonscapes far more diverse than expected. Even from a million miles away, the Voyager's instruments detected peculiar signals, leading to the discovery of active volcanoes on Io, which is now known as the most volcanically active body in the solar system. The particles ejected by Io's volcanoes give the moon its colors, with Pelée, one of Io's largest volcanoes, producing ash plumes 30 times higher than Mount Everest and covering an area almost as large as France. The Voyager probes captured over 33,000 images of Jupiter and its satellites, revealing new wonders with each shot. For example, Jupiter has rings and Europa, one of Jupiter's 53 named moons, has an icy shell believed to be over 60 miles thick. The spacecraft received a gravity assist from Jupiter, accelerating by 35,700 miles per hour and gaining enough speed to escape the Sun's gravity and travel to the stars. At Saturn, the Voyagers took separate paths. Voyager 1 flew past Titan, a moon veiled in a thick orange atmosphere, then ascended northward out of the planetary plane. After passing through Saturn's rings, it withstood numerous impacts from dust particles. Voyager 2 continued alone to Uranus and Neptune, discovering 10 new moons orbiting Uranus in 1986 and documenting winds up to 1,000 miles per hour as it passed Neptune in 1989. Triton, the largest moon of Neptune, was discovered to have one of the solar system's coldest environments. With a surface temperature of -391 degrees Fahrenheit, -235 degrees Celsius. Methane and nitrogen gases are present in its azure atmosphere, where ice volcanoes eject nitrogen gas and particles 5 miles high. Carl Sagan, a member of the Voyager 2 mission's imaging crew, pushed for capturing last images of Neptune and its moons before NASA planned to turn off the cameras once the Grand Tour was complete, with no further photo opportunities as the Voyagers moved into interstellar space. Sagan convinced NASA to let Voyager 1 take one final batch of images, resulting in the famous pale blue dot photograph of Earth from 3.8 billion miles away, the farthest image of Earth to date, appearing only as a faint, tiny speck hidden in sunlight reflected from the camera's optics. Both Voyagers now drift so far from Earth that a one-way radio signal takes almost 22 hours to reach Voyager 1 and just over 18 for Voyager 2, advancing by 3 to 4 light seconds each day. The Deep Space Network, NASA's global trio of tracking facilities, maintains their communication. However, as these faint signals grow weaker, hearing the spacecraft is increasingly challenging amid Earth's radio noise. Yet, these signals continue revealing unexpected findings about interstellar space, as both Voyagers cross the boundary of our solar system into interstellar space. The boundary of interstellar space, distinct from the solar system's edge, lies beyond the heliosphere, where the solar wind, a continuous flow of charged particles and magnetic fields from the Sun, encounters interstellar matter. This boundary, called the heliopause, lies around 120 km from Earth, as detected by Voyager 1, which confirmed an increase in plasma density, though no directional change in magnetic fields. When Voyager 2 crossed this boundary 6 years later, similar results puzzled scientists, contradicting predictions that expected the heliopause to move with the Sun's 11-year cycle. As Voyager's data refine models of the heliosphere's interaction with the interstellar environment, scientists propose that the Sun entered a region of partially ionized gas left by a supernova, affecting its magnetic field. These observations reveal turbulent, mixed magnetic fields rather than the smooth fields expected by theorists, suggesting the Voyagers might soon detect a pure interstellar magnetic field. Eventually, the spacecraft will move beyond this turbulence, becoming relics orbiting the galaxy for millions of years, long after the Sun and heliosphere have faded. Powered by plutonium's radioactive decay, each Voyager now operates only a few instruments due to diminishing power. Yet, they carry golden records, copper discs coated in gold with images, sounds, and music from Earth, including President Jimmy Carter's message of hope for future galactic civilizations. After 16,700 years, Voyager 1 will pass by Proxima Centauri, with Voyager 2 following 3,600 years later, carrying Earth's message in a bottle into the vast cosmos.